Hello, and welcome back to the course on classical electromagnetism. We are now on the fifth chapter for this course, which will be all about magnetic fields in matter. So the discussion here is actually just very similar to electric fields in matter, since electric fields and magnetic fields are basically symmetric. Electricity and magnetism are symmetric. So before we proceed, let us first review some of the concepts that we have discussed so far. So we have discussed about magnetic dipoles in the previous chapter. So we also have discussed about different types of magnetic materials. We have ferromagnets, diamagnets, and the most common, your everyday object, are paramagnets. So our bodies are paramagnets, and virtually anything that you see will most likely be a paramagnet. So in electrostatics, when we discussed about electric fields in matter, we discussed about the electric potential energy, which is the negative dot product of the dipole moment with the electric field. And the force for non-uniform electric field is just the negative gradient of potential energy, or the gradient of P dot E. And the torque exerted by an electric field on an electric dipole is the cross product of the dipole moment P and the electric field E. So we will actually be looking at the same or similar equations when we go to our topic, or to the first lesson of the chapter, which is on force and torque on magnetic dipoles. So magnetic dipoles can be created if you have a current loop. So if you have a bar magnet, that's also a magnetic dipole. So a magnet is always a dipole. There's no magnetic monopole, so it's always a dipole. So if you have a current loop, basically you have a magnetic dipole moment M. So basically your loop becomes a magnet. It has a north magnetic pole, it has a south magnetic pole. And its magnetic dipole moment is just equivalent to the current times the area vector. And if you expose this current loop in an external magnetic field, similar with the electric field, it will exert a torque on your dipole. So the torque exerted by the dipole is just the dipole moment across the field. So it's just very similar to electric field in matter, wherein the torque is just the dipole moment across the field. So similarly, magnetic dipole moment across the magnetic field. So similarly, the magnetic field will try to rotate dipole in such a way that its magnetic dipole moment will align with the external magnetic field. Similar with what happens in with electric dipoles. So the field will always try to rotate the dipole moment vector and align it with the direction of the external magnetic field. So the force on a dipole is zero if you have a uniform field. So similarly, that's also true for magnetism. So if you have a uniform magnetic field, then the force on the dipole is zero. But if you have a non-uniform magnetic field, then the force on the dipole will just be equal to the gradient of the negative gradient of the potential energy, where the potential energy is negative m dot b, or the cross dot product, the dipole moment and the magnetic field. So if you have an atomic dipole, for instance, so since this is the nucleus and this is an electron, the electron is looping around the nucleus, so creating an electron current loop. So basically, you have an atomic dipole. So in this case, the magnetic dipole moment is it actually the direction of the magnetic dipole moment actually obeys the right hand rule. So if this is the direction of the current, then this is the direction of the uh, magnetic dipole moment. But since electrons are negative, even though the electron current is in this direction, the magnetic dipole moment is in the opposite direction because it is negative. The right hand rule only applies for positive charges and positive current. If you have a negative current, such as an electron current, then you need to reverse your right hand. So this is the direction of the atomic dipole. So the atomic dipole moment is actually a combination of the orbital dipole moment, uh, the dipole moment of the electron with respect to the nucleus, and the spin dipole moment. Since the electron spins on its own axis, so it also creates its own magnetic dipole moment. So orbital dipole moment plus spin dipole moment. But the orbital dipole moment is actually very much greater as compared to the spin dipole moment. So if you expose this atomic dipole in an external magnetic field, not necessarily uniform, then the external field will exert a torque on the atom. But since it's hard to tilt the orbit than the spin, so only the spin dipole moment is affected, since it's hard to rotate this orbital dipole moment. So only the spin dipole moment is affected by the torque. So in this case, it's either the electron will speed up or slow down. So that is the effect of the external magnetic field on atomic dipole. So the change in magnetic dipole moment is actually proportional to the negative of the magnetic field. So this one. So the direction of the change in dipole moment is actually opposite the direction of the magnetic field. So if the magnetic field is in this direction, then the direction of the change in magnetic dipole moment will be in the opposite direction. So for paramagnetic and ferromagnetic object, the spin will actually align with the magnetic field. So usually, if you have odd number of electrons, and if you have diamagnetic materials, this is actually a reversal of spin, opposite to the direction of the magnetic field. So if you have even number of electrons. So let's have a first example. So find the torque exerted by the circular current loop on the square current loop. So you have a circular current loop with radius A, dipole moment M1, it's carrying a current I, and it's actually in the XY plane. So this is our XY plane, it's the Z plane, or sorry, the Z axis. The square loop is actually in the XZ plane. So in the XZ plane, so this one, it has a length of B and dipole moment M2 in this direction. So M1 is actually along the Z hat axis, M2 is along the Y hat axis. Okay, so in order to solve this problem, it will actually require us to solve for the torque exerted by the loop 1 on loop 2, so P12, and this is equal to the magnetic dipole moment of loop 2 crossed with the external magnetic field, which is the field caused by B1. So we need to solve for M2 and B1 first. So what is M2? The magnetic dipole moment of loop number 2, the square loop. So it's just current times the area vector of loop 2. So the area of loop 2 is just B squared. Its direction is along the Y axis. So you will get I B squared Y hat. Okay, so how about B1? What is B1? So B1, it's a dipole. So therefore, its magnetic field will be that of the dipole. So mu naught over 4 pi r cubed 3 m1 dot r hat minus m. Okay. So what is M1? M1 just current I times the area of the circular loop, which is pi a squared, and then its direction is z hat. So that is m1. What is r hat? R is the distance from the dipole 1 to dipole 2, and r hat will be from, since we are measuring the magnetic field of B1, so the origin will be from B1. That is r hat. So r hat is in this direction, it's in y hat. So r hat, I'm just going to put r1. r1 hat, so it will not be confused. So r1 hat will be y hat in this case. Okay, so you substitute this one, m1, that r1 hat, this is y hat, and this is z hat, and b1 will actually be, so you will have mu naught over 4 pi r cubed. Sorry, I'm just gonna give the final result. So 4 r cubed mu naught ia squared, and then negative z hat. So that's what. This is m1. So m1 dot r1, if you dot these two vectors z hat dot y hat, you will get negative x hat. Sorry, it's a dot product. It's a scalar quantity. So the dot product of these two is just I pi a squared. R1 hat is y. So sorry for that. So the dot product of z and y is 0. So basically the first term here will be, this will be 0. Since the dot product of two perpendicular vectors is 0. So dot product of a dot b is ab cosine theta. Cosine of 90 degrees is 0. So you are left with this one. So this is our B1 now at the location of loop 2. So we will use this B1 and we will use this M2. So M2 cross B1. So you will have y hat cross negative z hat, and that will give you negative x hat. So the final result will be this one. So that is the torque exerted by the magnetic field of the circular loop on the square loop. It's in the negative x hat direction. So this is positive x hat. So in the negative x hat direction, so it will actually, so B1 is actually in the negative z hat direction. So this is the direction of the magnetic field of loop 1. So it will try to rotate this loop so that its magnetic dipole moment will align with the magnetic field of B1 at this point. So at this point, the magnetic field of loop 1 is that one. Take note, this is dipole, so it's a magnetic field, something like that. It's curling around. Okay, so there's a second question. If the square loop is free to rotate, what will its equilibrium orientation be? So since if this is free to rotate, then this will align with the magnetic field here. So therefore, M2 final, the final position of the magnetic dipole moment vector will be IB squared negative z hat, since B1 is in the negative z hat direction. So that one, it will just align with the external magnetic field, which is due to the field of M1. So you can also do the reverse for this situation. What is the torque exerted by loop 2 on loop 1? So you can also do that. Okay, let's have a next example. So find the force of attraction between the 2-point dipoles. So in this case, what we are trying to find is the force of attraction between the two. So it's either we can solve for F, the force exerted by dipole 1 on dipole 2, or the force exerted by dipole 2 on dipole 1. Anyway, by virtue of Newton's third law of motion, the force exerted by 1 on 2 is has just the same magnitude as the force exerted by 2 on 1. They have the same magnitude but opposite in direction. So let's try solving for F12. So this will just be the gradient of M2 dot the external field, which is in this case is B1. Okay. M2 is clearly, say, assuming it's a magnitude of M2. Sorry. So M2 here, assuming that's a magnitude of M2, it's directed along the y-axis, so M2y hat. And B1. So what is now B1? So B1, again, we go back to the dipole formula. So mu naught over 4 pi r cubed. We have 3 m1 that r1 hat r1 minus m1. So in this case, we will assume that m1 is also a constant, has a constant magnitude. Say m1, its direction is also y hat. In this case, r1 hat. So from m1, that one, so r1 hat is actually y hat. So in this case, m1 dot r1 will actually be non-zero, since you have y hat dot y hat. So you will get, if you do this, you will get a final answer of mu naught m1 over 2 pi r cubed, and its direction is z hat. So take note, this is a dipole. Its dipole moment is actually like that, curling around. So at this point, its dipole moment is actually the direction of V1 is y hat. So this is a dipole, so its dipole moment, its magnetic field is somewhat like that. Along its axis, so it's straight, and then it will curl around. Okay. So it's y hat. So since R1 is y hat, and M1 is also in y hat, so y hat. Okay, that one. So you dot these two, M2 dot B1, and you will get, and you take the gradient on that. So in this case, our R, the magnitude of our R, is actually, since this is along the y-axis, we can actually replace R by y, since our R is actually y. Our R only has a y component. It doesn't have a z component, it doesn't have a z component. It's only purely y component. So you dot this two, and you take the gradient of that. So in this gradient here, only the y component. So you will get F12 will be the gradient. So in this case, it's partial with respect to y of M2.B1. So if you dot this two, you will get mu naught M1 M2 over 2 pi y cubed. And this is just the y component, so y hat. So for the gradient operator, only the y component will survive. The x and the y component will not survive because there's no x and y terms. So that one. So take the derivative of that with respect to y. So this actually now becomes a total derivative, no longer a partial derivative. So derivative y 1 over y cubed is negative 3 y to the negative 2 over y squared, or sorry, y to the 4th. So in this case, our F12 will be equal to 3 mu naught M1 M2 over 2 pi. I will just go back from y to r, so r to the 4th negative z hat. So that one. So in this case, the magnitude is just this one, this term here. So the force exerted by dipole 1 on dipole 2, it's just opposite in direction but equal in magnitude to the force exerted by dipole 2 on dipole 1. And it has they have the same magnitude, 3 mu naught m1 m2 over 2 pi r to the 4. R is actually just equal to y in this case. So what will happen? What happens is, sorry, I made an error. It's negative. The direction is negative y hat. Okay. So what happens is dipole 1 will exert a force on dipole 2 and its direction is negative y hat. So the direction is actually in that direction. That's negative y hat direction. So it's attractive. M1 will attract M2. And in the same manner, M2 will also attract M1. So the direction of F21, this is actually positive y hat in that direction. Okay, so that ends our first lesson. So for the next lesson, in the same manner as our discussion in electrostatics, we will be talking about how to find the magnetic field of magnetized object. So the electrostatic equivalent of that is how to find the electric field of a polarized object. So in our case, in the next lesson, we'll try to find the field, magnetic field of a magnetized object. So I will see you in the next lesson.